The name is bond, chemical bonds. Okay, enough of that. As we move into our next video, we're now going to focus on bonds, those relationships between atoms that are so important for making up molecules that we'll discuss in A&P and beyond. So in this video, bonds and chemical reactions, you should be able to describe the different types of chemical bonds, describe their relative strength, understand that bonds exist between atoms because of the electron shells, and we'll briefly touch on that, and describe a chemical reaction as the formation, breaking, or rearranging of chemical bonds. So what is a bond? A bond is not quite like this. It is not going to be a, a physical attachment so much as a energy relationship between atoms, specifically between the electrons of atoms. And what do we mean by this term, energy relationship? As you'll see in the next few slides, it's going to be how the atoms interact because of their electrons. And here we're going to be taking a shortcut. If you have chemistry, you'll get into far more details about atoms and electron structure than we're going to do here, but we'll do enough so that you understand what bonds are. Okay, so I have here a shell game. What you'll get into in a discussion, and let me come up here for a second, what you will get into for the discussion of looking at electrons and atoms in your book is you'll see all these concentric circles. These circles are trying to represent, you see them here, these circles are trying to represent the orbiting electrons of an atom. In reality, what's so important about atomic bonding is how these electrons of this particular atom interact with another one. But I don't want you to get too stressed about this. In fact, I'll give you a phrase here. The chemical properties of elements differ largely because the number and arrangement of their electrons differ. That is actually a simplified way of thinking about atoms, electrons, and bonds. That may not seem too simple, but look at it again. The chemical properties of elements differ largely because of the number and arrangement of their electrons. Why is nitrogen different than carbon, different than lithium, different than oxygen, different than all of them? Because their electrons are a little different in terms of the number they have, and maybe these shells. We have the shells here. We have one electron, for example, in this shell. Maybe another one has 2 electrons or 3 electrons in its shell. And that is largely why elements have different abilities to bond to other elements. That's very critical. Moving on, here we go. So let's look at the three main kinds of bonds. Again, bonds are energy attractions between different atoms. The first one is one that kind of piggybacks off of our discussion we saw in the first video, ionic bonding. Ionic bonding, surprisingly enough, is the bond that forms between ions. We recognize our friend here, sodium, and our friend chlorine. What happens in ionic bonding is one atom, in this case the sodium, will lose an electron and become positively charged. The chlorine will gain that electron and become negatively charged, and because they have opposite charges, they attract. Because one became a cation, one became an anion, that attraction is an ionic bond. It's an energy relationship because of their opposite charges. My animation here is not working, but if it was, you'd see the sodium would lose its electron here, and it would join the chlorine there. Now, for those of you who have a little more background in chemistry, you'd recognize that this would, quote-unquote, complete the shell for chlorine, and it also empty a shell for sodium, making it more stable. We are not focusing on that, so don't let that bother you too much. The point of ionic bonding is it's a bond between ions, an attraction between ions. So once sodium forms an ion and chlorine forms an ion, their opposite charges cause them to attract to each other and form an ionic bond. Oh, wait, there it goes. There's my animation. You see it going there. Finally. Let it run for a second so you can see it again. Notice how the yellow electron is being transferred to chlorine. Sodium is losing it, chlorine is gaining it, and therefore that what they're calling an electrostatic attraction is the ionic bond. Okay, it doesn't just have to happen between sodium and chlorine, that is one positive and one negative. Here is a case where calcium, grab my here, calcium, this particular atom or element rather, is going to lose 2 electrons from its outer shell, and chlorine will gain 1 and another chlorine will gain 1. So now calcium actually lost 2 electrons, so it's a positive 2. Remember, it lost a negative, so it becomes positive. Each chlorine gained a particular electron. So now 2 of these chlorines, and that's why the 2 is shown here, is the chlorine now each picks up an electron, a negative charge. So now calcium and will attract a chloride here, and there will be an ionic bond formed here and one formed there. And we will have, it's not written here, let me write it for you real quick. It could be written CaCl2 to show this ionic salt. Okay, so the point here is ever how many electrons are lost, now that many bonds can be formed between ions that pick up those electrons. Okay, going ahead. Oh, well, so would these be strong or weak bonds? Well, that's a good question for us to ask. If you have this attraction between a positive and a negative, this will be a relatively strong bond. Will they break easily in water? The answer is yes, and you'll see why when we get to our water topic very soon. We'll look at water structure and water properties, and you'll see that in fact ionic bonds do break in water. So here the name is bond, ionic bond, taken, not shared. The point of this little cartoon is that the electrons get transferred from calcium in this case to the chloride ion, and that's why this taken is referring to the transfer and not the sharing. That's important because a different kind of bond, covalent bonding, is when the electrons are shared. Important word, shared between 2 different atoms. So in this case, CH4 here, this is methane. In this case, this carbon here, pretend if you want to that it has all these red, the red ones are representing the carbon's electrons. In this case, carbon has 4 electrons in its shells, hydrogens just have 1. And again, if you have some chemistry, you recognize that 8 is sort of a magic number in chemistry. But the point here is notice how the electrons didn't get transferred from carbon to hydrogen or vice versa. They're sort of in this middle zone, they're being shared. And this gives us a different kind of bond, a covalent bond. Rather than transferring and taking electrons one from another, they are sharing. Here's carbon dioxide, CO2, and notice we have more electrons being shared here than we have over here. We only have 2, we have 1 pair of electrons. Here we have 2 pairs. Don't worry about the difference for right now, but because oxygen didn't take them and from carbon or vice versa, this is a covalent bond rather than an ionic bond. Covalent bonds, though, can actually be a little more involved, as you just saw. You can have a single pair of electrons being shared, as you have here in hydrogen. they're just drawing these as balls representing the atoms themselves, but they're sharing one pair of electrons. If you want to imagine that there's an electron here, an electron there. In the case of an oxygen double bond, that means they're sharing two pairs of electrons. Kind of hard to draw that. In nitrogen, they're sharing three pairs of electrons, and that's why that's a triple bond. As you might imagine, hydrogen bonds are going to be quite strong because you're sharing electrons. Oxygen with this double bond will be even stronger. Nitrogen, a triple bond, is even stronger than that. If you look over here, here's guanine. We'll work out what guanine is a little bit later. But notice in a molecule, you may have single bonds like you have here between nitrogen and carbon, and double bonds like you have here between carbon and oxygen. Are these going to be strong or weak bonds? Covalent bonds are quite strong, quite strong. Not all covalent bonds, though, are quite the same. There are sometimes when the sharing is not quite equal. We refer to a term called electronegativity, which means, oops, wrong one, let me erase that. Electronegativity is a reference to how well or how hard do atoms pull on electrons. Not all atoms have the same strength to pull on electrons. For example, if you had this case where you had a hydrogen and a hydrogen sharing a pair of electrons, and they're each sort of pulling on that pair because you have one hydrogen and another hydrogen pulling, they're going to pull pretty equally, so that's referred to as a nonpolar covalent bond. That is, if you imagine the electrons are sort of being shared right in the middle of those atoms, that's a nonpolar covalent bond. Different than here, chlorine is a very good electron puller. It's very electronegative. Therefore, while they are technically sharing a pair of electrons, the chlorine atom is able to pull the electrons closer toward it, and that's called a polar covalent bond, and that's important, as you'll see in 1 second. What happens if electrons are pulled unequally in a covalent bond? That is, in a polar covalent bond. Here's oxygen and here's hydrogen. And they've sort of given it away by how they've drawn this. But rather than the electrons being here, where they're equally shared, we have the electrons are being pulled by oxygen toward it. Oxygen is more what? It is more electronegative. So as electrons are being pulled toward oxygen, what kind of charge does oxygen take on if electrons are being pulled very close to it? Oxygen takes on a partially slight, small negative charge because it's got negative particles close to it. And we draw this delta minus to show it's slightly negative. If I pull electrons away from something, what is the resulting charge of hydrogen? If you pull electrons towards something, it becomes a little bit negative. If you pull electrons away from something, hydrogen becomes slightly positive. Okay, why does that matter? The last type of bond, the hydrogen bond, is a result of polar covalent bonds. Okay, think about this. If oxygen becomes a little bit negative because it pulls electrons close to it, and hydrogen becomes a little positive because electrons got pulled away from it within this polar covalent bond and within these polar covalent bonds, this negative and this positive slightly attract one another, and that forms our last type of bond, a hydrogen bond. A hydrogen bond is a weak attraction. I gave it away down here at the bottom. It's a weak attraction between hydrogen that's slightly positive and some other negative atom. So in this case, these are two water molecules. Here's hydrogen, and here's hydrogen, and here's hydrogen, and there's hydrogen. This is oxygen. This is oxygen. So as within this molecule, and let me switch pens, within this molecule, this becomes a little negative, that becomes a little positive, that becomes a little positive because of the polar nature of this covalent bond set. This becomes positive, this becomes positive, this becomes negative because of this polar covalent bond. The result is this positive and this negative slightly attract one another, and that is called a hydrogen bond. Would these easily break in water? These are very weak bonds, and so the answer is yes. Okay, and our last little bit here is looking at chemical reactions. As you'll see in A&P, we talk a lot about chemical reactions in physiology. What we're going to have in this case is a definition of chemical reactions simply being whenever chemical bonds are made or broken or rearranged. You see on this slide, we have methane and oxygen. Methane is CH4, C1, 2, 3, 4, and here's oxygen. These are reactants. This is the initial parts, if you will, the stuff we're going to work with. When these react, it's going to form carbon dioxide and water. If you count 1, 2, 3, 4, there's 4 oxygens on the product side. 1, 2, 3, 4. There's 4 oxygens on the reactant side. There's 1 carbon here. There's 1 carbon there. There's 4 hydrogens here. There's 4 hydrogens there. So this is a chemical reaction because the bonds are broken and then rearranged. And let's see if my animation works on this one. There we go. And all it's showing here is that temporary connection when the orange and red lines appear is showing you a bond is made. And you can tell me what kind of bond that is because the electrons are being shared. That would be a what kind of bond? Sure, that would be a covalent bond. Okay, that is going to finish up this video. And at this point, there will be an assignment, a coaching assignment to let you practice what you've learned.